Hello. Today we shall be speaking about other methods of integration. In other words, pursue the explanation about different methods in order to calculate integrals of functions. Now, the last one we spoke about, which is integration by substitution. Actually, this is the most widely used method. And yet, there are other methods, of course. One of them is the one that we shall be exposing today. It's called integration by parts. And integration by parts actually is one method that you can directly, you may be confused which method or the other, which you shall have to use, considering that you have some different kinds of functions at hand. But this one you can directly notice when it is the most convenient way in such a situation. Now, first of all, we shall be stating when this method is to be used, and then we shall be forwarding a mechanical technique of using it, and then we shall be speaking about a reduction formula concerning this method, and finally we shall be exposing some of the this is another method, but we extended it in other words, we shall speak about it later because it concerns square roots or roots of functions that we have been that they have been dealt with using also the method of integration by parts. Now, for this method, which is integration by parts, when is it to be used, and how do you know, for example, that it's convenient or the suitable way in your for a certain or for a particular function that you have? And usually, you can directly conclude that the integration by parts method is the suitable method when you encounter integrals of this form. When you have a product of two functions of different kinds, then the only method which is suitable or which can really solve your problem or which can render your integration possible is the method of integration by parts. For example, here you have an algebraic function and transcendental function. When you have x sine x or x product of x cosine x or x times e to the power x or x times logarithm x, or e to the x times cosine x, all these functions, because they are product of two functions of different nature, then the method that is suitable here, or I would say the only method which can really resolve your integral, or you can calculate your integral, is via the method of integration by parts. Now, as well here also sine minus 1x, which is the inverse function of the sine function, also the integration by parts can solve this integral. Why? Because when you substitute x is equal to sine y, you get dx is equal to cosine y dy, whereas sine minus 1x becomes y. So actually this here resembles the same one here, or the same one here, x sine x or x cosine x or y cosine y, etc. All these are similar, and therefore all these 5 integrals, the only way by which you can calculate these integrals is via the method of integration by parts. The method relies upon the derivative of a product of two functions. When you have, for example, f and j, now you know that the derivative of the product is equal to f dash of x times g of x plus f of x times g dash of x. Now, this is the formula we shall be using in order to extract the law that we shall be using in the integration by parts. Now, here what we do is that you get one, for example, this one, we take it to the left-hand side, and you end up with what? You end up with let us write it down. Now, you have here f, the integral of f of x times g dash of x is equal to, dx is equal to what? Is equal to the integral of d by dx of f of x times g of x minus the integral of f dash of x times g of x dx. Now, this is the law that you shall be using, in fact. So here, this becomes what? This part here becomes equal to this one here. The integral of a derivative, and we saw this before, is equal to f of x times g of x. So you have here minus the integral of f dash of x times g of x dx. And that's the law we shall be using. So what you have here is that the integral of the product of a function times the derivative of another function is equal to the product of the two minus the integral of the first function differentiated times the other function. Of course, you can add a constant c. Now, if you take, for example, f of x is equal to u and g of x is equal to v, you end up with the following integral. Here you have u, and this gives you what? This gives you g dash of x becomes equals to v g dash of x dx is equals to dv, because since v is equal to g of x, then dv by dx is equal to g dash, or that g dash of x dx is equal to v. So you can substitute this part here by what? You can get the law will be in this form, u dv. It's equal to what? Here, u times v minus the integral of what here? You have g, which is v, then you have f dash of x dx is equal to what? To du. So this is the law we shall be using. So the integration by parts will be carried out in this form. You have the product of two functions. One of them is f, and the other one is v. And you have to choose, while you are carrying out the integration, you have to choose which to call it u and which to call it v. And here is your law. As I said, you take u, for example, is equal to f, and v is equal to g, and you get this theorem here. If u and v are differentiable functions of x, and on interval I, then the integral of u dv, it's equal to uv minus the integral of v du. Now, we wish to apply this on some integrals. For example, here, evaluate the integral of x times e to the x dx. Now, suppose we want to tackle this problem. Here, again, the integral of x times e to the x dx. Now, suppose here I take u is equal to e to the power x. This is u. So where is v then? It tells you the integral of u dv. Then if this is u, then v, so you take, actually here, we shall summarize here, you take u is equal to e to the x, power x, and v is equal to what? Half x squared. Why? Because here you want u dv. Let us calculate u dv, u, which is e to the x. What is dv here? dv by dx is equal to x. So dv is equal to x dx. So actually, you end up with the integral above here. So if you take u is equal to e to the power x and v half x squared, you end up with x e to the power x dx is equal to u dv. Now from the law, you have this is equal to uv minus the integral of v du, which is equal to, where is u v? You multiply these together, you get half x squared e to the x minus the integral of v half x squared du, which is what? Which is e to the x dx. So now this is the integral that you obtain. But as a matter of fact, this is more complicated. Now you started with the integral of x times e to the power x dx, and you ended up with, you want now to calculate the integral of x squared e to the power x, which is more difficult. But then if you take the other choice, you interchange these two variables here. Instead of taking u is equal to e to the power x, you take v is equal e to the power x. In other words, again here, you have x times e to the power x dx. And you choose the following. You choose that u is equal to e to the power x, and v is equal to, you have here u equal e to the x, and you take v is equal e to the power x. Now let us calculate u dv. Now u dv is equal to the integral of u, here u, and times dv. dv is equal, v is equal to e to the power x. So dv is equal e to the power x dx. So actually, this is the integral you wish to calculate. This would be equal to u times v, which is x times e to the power x, minus the integral of v, which is e to the power x, du, which is dx. Now look how easy it is now, because here you have your integral have become x times e to the power x minus the integral of e to the power x dx, and this is directly equal to e to the power x, because the integral of e to the x is equal to e to the x. So actually, this is the result of your integration. And to make sure that this is correct, what you do, you differentiate it. If you differentiate it, what you get the derivative of the first one times the second one, plus the first one times the derivative of the second one, minus e to the x. And actually, you get directly here the integral, your function which you have started with. So you see now the choice of u and v, either it simplifies your integral or it makes it more tedious to calculate it. So you have to make sure, and this actually depends on, usually you take the one of u, the one that usually can finish easily by integration. So we'll see another one. Now here, x times cosine x. So what you take, for example, u is equal to x, and v is equal to sine x. Now, what is the integral of u dv? The integral of u dv is equal to u, which is x. This is x, u, dv, d sine x, which is cosine x dx. So actually, u dv is the integral that you started with. Is equal to what? Is equal to u times v. In other words, x times sine x, minus the integral of v times du. v, which is sine x, du, which is dx. So you see now, it has been much simplified. So your original integral will become equal to x sine x minus the integral of sine x, which is minus cosine x, and you end up with this integral. So you see the choice of x and v is crucial in order to simplify the integral. Here again, this is easy because you have one function. So you choose this u, ln x is equal to u, and v is equal to x. So again, you have here the integral. What you have here is u dv. So u dv is equal to u times v, which is x ln x, minus the integral of x of v d of ln x. Now d of ln x is equal to what? Is equal to the derivative of ln x times dx. The derivative of ln x is 1 over x. So this cancels out here x, and you end up with dx, which is 1 integrated, gives you x, and you get directly the integral at the very end. So you see now that you have to make sure which to use and which to keep, which to use as u and which to use as v. Now this one is a little bit complicated. Suppose, for example, you want to integrate e to the power x sine x dx. So for example, you choose v is equal to e to the x and u is equal to sine x. So what you have here, you have u dv, which is e to the power x dx. So in fact, u dv is equal u times v. You calculate the product of these two, which is e to the power x sine x, minus the integral of v, which is e to the power x, d of sine x. d of sine x is equal to what? Is equal to cosine x dx. And you end up with this form here. But again, this form is not the end, because you have to integrate again e to the power x cosine x. So what you do, you have to renew your calculation. You take, for example, v is equal to e to the power x, and u is equal to cosine x. So here this becomes u dv, which is again equal to, here it is, u times v, which is cosine x times e to the x, minus the integral of v, which is e to the power x, d cosine x. d cosine x is equal to what? Is equal to minus sine x dx. So invert the sign here. But then you realize something, that you have almost solved your problem. Why? Because you have started with the integral of e to the power x sine x, and now you end on the right hand side, you have the same unknown here. So what you can do with a negative sign, you can actually sum up the two integrals together. Here you have the integral of e to the power x sine x, and here it's again the same integral. So you can sum up both to obtain twice the unknown integral which you wish to calculate is equal to the sum of these two terms here, which is e to the power x sine x minus cosine x, or the integral that you wish to calculate is equal to half this expression here. Now, finally, for example, you have the integral of 1 minus x square root of minus x squared dx. So which you choose a u. This would be u, and this would be v. v is equal to x. So we will tell it directly. Now, the integral of u dv is equal u times v minus the integral of v d of the square root of 1 minus x squared. But the square root of minus x squared, when it's differentiated, you get what? 1 over twice the square root times the derivative of what's inside. This is the chain rule. So here 2 cancels out with 2, and this sign here because you get the derivative of minus x squared. So you end up with what? You end up with x times square root of 1 minus x squared minus x times minus x divided by 1 minus x squared. What you can do here, you have here minus x squared. So you can add 1 and subtract 1. When you add 1, you get 1 minus x squared divided by square root. So you get the square root here again, and there remains 1 divided by the square root. Now here you notice again that the integral you started with is the square root, and you end up here with the same square root. So what you do is that you move this to the left hand side to get twice the integral. It's equal to this expression plus the integral of 1 over root 1 minus x squared, which is again you can open up your book and you find directly this is the inverse function, the inverse sign of minus 1x, and therefore your integral is half this piece here, this expression here, plus sine minus 1x. Now these are square roots, integrals which contain square roots, and they are tedious, and therefore we shall forward a simpler way to deal with these kind of integrals. But then I want to say something important. Now there is a mechanical technique which we use all the time, instructor they use for the students. Instead of choosing u and v, etc., we'll show you a very simple way for amenable to a simple calculation that would help the student understand more the subject. Now here it is the mechanical way. It tells you the following. If you have an integral of the product of two functions, what you do, you say the integral is equal to the integral of the first one. You integrate one and you leave the other one without change. In fact, this is exactly compatible. This is exactly similar to equivalent to the one that we have just showed, except that the one we have just explained, the problem is that you are confused which to choose as u and which as v. But here you get directly the insight as to when you apply the law, it goes automatically. You proceed directly, or you follow the right track in this case. So you integrate one, and the other one you set it without change. Minus again the integral of, you integrate again the first one, whereas the second one you differentiate it. So the rule is the following: the integral of product of two functions is equal to the integral of one times the other one without change, minus the integral again of the first one times the derivative of the second one. And we shall see how to apply it easy. Now you wish to evaluate, for example, the first one, which is the integral of x times e to the power x dx. Now what you do, suppose we go back to the slide. Now we take the integral of 1, which is e to the power x, times the other one without change, minus the integral, again, like this one, of the first one, times the derivative here of the first one here, of the second one. So derivative of x is equal to 1. So one you integrated, the one and one you keep, minus the integral, again, the one that you integrate, and the other one which you have kept before, you differentiate it. So directly you get the integral of e to the x, and that's the result directly. Let's take another example. Now the logarithm of the integral of 1 times ln x, what you have here, the integral of 1 you add times the second one. So we do it again. Now you have here two functions. One function ln x. What you do to help yourself, you add 1. So you have now two functions. One you integrate, and the other one you leave it as it is, minus the integral of the one that you integrated, you put it again as x, times the derivative of the second one, which is ln x, which is 1 over x. And of course this cancels out, you get 1, and you get direct the integral. So the procedure is simple. One you integrate, the other one you leave it as it is, minus the integral, the one that you integrate, you put it again, times the derivative of the second one, and that's your integral. Here there is even a better way. People who have witnessed or have remarked, who have noticed the same remark we did now, that one you integrate and one you differentiate, they said to themselves, why don't we, for example, have a table of two, for example, you have two columns, one the function that you want to differentiate and the other one you want to integrate. For example, this you integrate and this you differentiate. Why you choose to differentiate x squared? Because it's going to be cancelled, depleted, finished. So here you integrate e to the power x, you integrate it again, and you integrate it again, and you keep integrating it, while the first one you differentiate it twice to get 2x, you differentiate it twice to get 2, and then it's 0, which is the third derivative. Now the product, now the integral is directly the following. What you do, you multiply x squared here times the first integral with a positive sign. And then the next sign is negative, plus 2x times e to the power x, but with a negative sign, plus the 2 times e to the x, etc. And you get this one here. So actually what you do here is that you integrate this times this minus the integral of this times the derivative of this, etc. In other words, let us do it this way. You have x squared e to the x dx. What you do, you choose one to be integrated. So you say, you integrate e to the x times the second one without change. Now the integral of the integrate the first one again, which is this one, times the derivative of x squared, which is twice x dx. Now you do it again, e to the x minus twice here. You integrate this one, e to the x, times this one without change, minus the integral of, you integrate again this one, times the derivative of this one, which is 1 dx. So what you have here finally, x squared e to the power x minus twice x e to the x, and then plus twice e to the x. Let's see if this is right. Correct. So, but this is actually is easier. Why? Because even you don't have to go ahead with the integration. You just can have it as 2 tables, and from the table you can choose directly what to do. Here, for example, you want to integrate x cubed sine x. So one you integrate, which is this one, and one you differentiate x cubed, 3x squared, 6x, 6, etc. So you multiply the integral. The result would be x cubed times cosine x, and you have positive here, because here you have minus cosine x already, so you have minus. Minus, this time, 3x squared times minus sin x. So you get 3x squared plus sin x. And then now it's plus 6x times cosine x, and then minus 6 times sin x, and that's your result. So this is a mechanical way of doing it. Now sometimes you instead of this, sometimes you don't want to pursue the operation till the end, because sometimes it doesn't end, like for example e to the x cosine x, those sort of things, or you don't know the power. For example, you want to integrate, for example, x to the power n e to the x. It's not x cubed or x squared. So you need some recurrence formula in which you store it aside in case you want, for example, to calculate it for a particular value of n. So what you do here, you obtain what is known as a reduction formula. So let us do it using the mechanical procedure we had before. You integrate one and you differentiate the other one. So now here, this is the solution. Here, you integrate e to the power x times the second one without change, minus the integral of the first one here, you integrate it, times the derivative of x to the power n, which is n x to the power n minus 1 dx. So what do you have here? You have the integral of in, in other words, this is the integral that you started with, to a power n. You call it in, symbol here stands for this particular integral. When the power is n, it's equal to e to the power x, x to the power n, minus n times the same integral. This is the same integral which you started with, except that instead of n, you had n minus 1. So you had a form of this sort. In is equal to e to the power x, x to the power n minus n, in minus 1. So suppose, for example, now you wish to calculate the integral x to the power 7 e to the x dx. So what you do, you directly come here and say x to the power 7 times e to the power x dx is equal to x to the power 7 e to the x minus 7 I6. And what is I6? The integral of e to the power x, x to the power 6. But this is again equals x to the power 6 times e to the x, and so on. So your recurrence relation, here it is. You have here, this is the first recurrence relation. The integral of this integral is equal to x cubed e to the power x minus 3i2. But what is i2? This is the integral of x squared e to the x. But x squared e to the x, you got this integral here. So you reduce, instead of n equal to 3, you have n equal to 2. And instead of n equal to 2, you have n equal to 1. And instead of n equal to 1, you have n equal to 0. It means that x to the power 0 times e to the power x. In other words, you have only the integral of e to the power x, which is e to the power x. So you end up with the whole integral. Now, usually we use reduction formula when you are not sure about the power here. So that you have it in case you want to use it several times for different values of n. For example, here we want a reduction formula for ln x to the power m. In other words, somebody asks you, for example, get me the integral obtained of ln x to the power 6. what you do, then you use a formula of this sort. Here, what you do is that you say, this is one function, you add up one here. Why? Because you wanted to apply the rule. The rule concerns product of two functions. So if you put one here, and then you use our law, you say, the integral of one, which is 1, you get x, times the other one without change, minus the integral, again, of 1, which is x, times the derivative of ln x to the power n, which is m, this is the chain rule, times ln x to the power m minus 1, times the derivative of g, which is what? Which is du by dx, which is ln x, derivative of which is equal to 1 over x. So x cancels out with x, and you end up with this formula. Now, this formula, if you want to read it correctly, this im means this integral, whereas this ln x to the power m minus 1, it is the same integral. However, instead of writing m, you have for an index m minus 1, it means that we can express it as im minus 1. So when you have, for example, ln to the power 5 dx, and you wish to calculate this integral, you say directly that the integral of ln x to the power 5 is equal to x ln x to the power 5 minus 5 times I4. But what is I4? I4 is equal to x times ln x to the power 4 minus 4 I3. And what is I3, etc., until you end up at the very end, which is the integral of ln x, and we saw before that the integral of ln x is equal to x ln x minus x, and this is the way you can do to resolve any or to calculate any integral where there is an index and you wish to calculate it several times for a few of these exponents which differ every time. Now, we saw in one of the integrals here that we had an integral of the square root of 1 minus x squared dx, and we said that we follow the integration by parts. So we said that the integral of 1 x times the integral will become times the other one without change, as I said, minus the integral of x times the derivative of this one, which is what? Minus x divided by the square root of 1 minus x squared. Exactly, and here you have minus x squared. So what we did, we added 1, we subtracted 1 divided by square root 1 minus x squared, and this is the way we did it. 1 minus x squared minus the integral, the integral of 1 minus x squared plus the integral of 1 divided by 1 minus x squared. This is what exactly we did it by integration by parts. And then here, this is what we started with I. This is the integral we want to calculate, and this is again the same integral I. So actually, as a matter of fact, when you notice here the last line, you can read it in this form: I is equal to x times the square root of 1 minus x squared, and then you have the integral. You moved it to the left hand side, and plus the integral, I suppose, of the 1 over the square root of 1 minus x squared. I think this is the last line we had. Now this is equal to what? To arc sine minus 1x, and directly your integral is equal to half of the square root of x minus x squared plus sine minus x, and this is the integral that you have started with. But this is complicated, really. So the best way of doing it, why don't we do it in otherwise? Why don't you do it in this way? You have an integral 1 minus x squared. I am going to do a substitution. The substitution will be the following. I will take x is equal to sine theta. Of course, this is not the only substitution. You can take sine or cosine. Suppose I take x is equal to sine theta and see if this is much easier. Now, if x is equal to sine theta, then dx by d theta is equal to what? Cosine theta. Theta is only a variable, dummy variable. So this becomes cosine theta d theta. And the integral becomes what? Square root of 1 minus sine square theta times dx, which is cosine theta d theta. Now, this is equal to what? 1 minus sine square is equal to cosine square under the integral sign. It's equal to what? You remember, it's equal to mod cosine. But if we are considering only the interval from minus pi by 2 to pi by 2, the mod cosine is equal to cosine. So you have cosine and cosine, and you have cosine square theta d theta. So how easy it is. So instead of doing integration by parts for this particular integral, you can do some sort of substitution in order to transform it into a cosine square. And the cosine function square, there is one way of doing it. You integrate it by replacing cosine square by twice the angle d theta, and this is equal half theta, and this is equal to 1 over quarter sine 2 theta, and it's finished. So actually, this is much easier to do than integration by parts. In other words, when you have square roots, instead of integrating by parts, you can use a kind of substitution. Now, these are integrals of the form. This one or this one and this one. These are, instead of, you can use integration by parts, but as I said, there are much easier way of handling these kind of integrals. For example, this one you can, the idea in textbook, in English textbook, they call them trigonometric substitution. I call them removing the square root, because the substitution that you choose is the one suitable to remove the square root. For example, here you want to remove the square root. How would you remove the square root? By which substitution? If you choose x is equal to a sin theta, then you have here a square minus a square sine square theta. So you get a cosine theta directly. So you have moved the square root. And here, how can you remove? You put here x is equal to tan, a tan theta, whereas here you put x is equal to a sec theta. So you choose a particular substitution, any substitution. Not necessarily here, for example, sine. You may choose the cosine. Or you may use, for example, the cotangent, for example, substitution, or the tangent. In other words, you choose a particular substitution, or here, for example, you can use the sine hyperbolic, because 1 plus sine hyperbolic square is equal to cosine hyperbolic. So you choose a particular substitution in order to remove the square roots. Now, suppose you have an integral of this sort. So a substitution x is equal to a sin theta. All those substitutions are suitable to replace x here. You can use this substitution in order to remove the square root here. Any one of them is suitable. Suppose we take x is equal to a sin theta. So we get dx is equal to a cosine theta theta. Here it is. Here you have a, and then you replace x by a sin theta. You have a square minus a square sine square theta. So you have a times a is equal to a square. Now 1 minus sine square, as we said before, is equal to cosine square under square root. You get mod cosine. If cosine range from minus pi by 2, theta from minus pi by 2 to pi by 2, you get cosine times cosine square square, and it's finished. Now from this onwards, you can now consider replacing cosine square theta by half plus half cosine twice theta, and you carry on the integral. So this is one way of removing square roots, as I said, or using trigonometric substitutions instead of using the integration by parts, which is also good, except that it is more tedious. Now, these are the kind of substitution that usually, for this substitution with the sine, as I said, for this one, the tan will remove the square root, whereas here, the secant, which removes the square root. Now, suppose you have an integral of this sort. What kind of substitution will remove the square roots? Of course, x is equal to 4 sin theta. Now, once you've chosen the substitution, you have to remind something. Here you choose x is equal to 4 sin theta. You have directly to draw a certain triangle. You have sin theta is equal to, here this is x, and this is 4, and this is square root of 16 minus x squared. In other words, your substitution implies directly, impose upon you that you choose the triangle in which you shall know where is theta, because since sin theta is equal to x divided by 4, I'm sorry, actually I did a mistake, because sin theta, this is theta, so this must be x, and this must be 4, and this must be the square root of 16 minus x squared. So sin theta is equal to this. So once, if the integral gets you, for example, tan, you know what to replace tan theta in function of x, or cosine theta as a function of x. Now here, directly, you have, once you do this, what you get here? You get, in the numerator here, you get dx. So since x is equal to 4 sin theta, then dx is equal to 4 cosine theta. And instead of the numerator here, you get, because when you, let's go back to the slide here, you replace x squared by 16 sine square theta. While you replace here 16 minus 16 sine square theta, so you get what? 4 cosine theta. And you get an expression of this sort. Now cosine theta, they cancel out, and you get 1 over sine square, and the 1 over sine square is cosec square, and you know that cosecant square, the integral is equal to minus cotan. Once you get the final answer here, you have to go back to your triangle here. Your triangle tells you that the result is cotan. Where is the cotan? It's this expression, this square root divided by x, and this is your result. So to deal with square root, as a matter of fact, this square root, the best way of dealing it is through some substitution which remove this square root, and this is called in English textbook trigonometric substitution. Let's take another example. This is 1 over the integral of 1 over x squared minus 1 to the power 3 by 2. Now, which substitution can remove this square root here? the secant would do. Why? Because sec square minus 1 is equal to 10 square. So directly, if you use the substitution, let us do this integral directly. You have the integral of 1 divided by x squared minus 12 to the power 3 by 2x. So it becomes directly, the x is equal to sec theta, so you have dx sec theta tan theta d theta, and you have here 1 over x squared. X squared is equal to what? Sec squared theta minus 1 to the power 3 by 2. So the integral become, here you have tan squared, so you have tan cubic theta times sec theta tan theta d theta. So the integral becomes what? Tan goes with tan, so you have sec theta divided by tan squared theta. And from this onward, you can proceed by replacing tan squared theta by sine square over sine square. But you have to remember something. Once you choose the substitution, like for example in this case, if x is equal to sec theta, so your substitution here is x, here is theta, so this must be x, and this must be 1, and this must be square root of x squared minus 1. Like this. So once your result here, you substitute tan square by sine square over cosine square, and cosine square cancels out with 1 of the sec, so you get at the end cosine over sine square, and this is by the chain rule, the integral is equal to minus 1 over sine theta. But then you have to replace this in terms of x. You go back to your triangle, then what is the value of sine? It's this one over divided by this one, so it's the opposite, so it's x divided by the square root of x squared minus 1. And this is how you do it. For example, this is another one here. Which substitution can get rid of the square root? Of course, it's e to the x times e to the x equal to sine theta. When you do this, you follow the same line of approach here, and you do the same thing. With this, actually, we come to the end of our lecture, and this form of this method of integration by parts, usually books usually they explain this thoroughly, because this is one of the methods which is very efficient and very strong and can deal with a variety of functions. But the main thing is that you have to memorize is that when you have an integration of two functions, f and g, f of x times g of x dx, and this is actually instead of taking one is equal to u and the other one g of x is equal to v and using the formula u dv and v du, no, you memorize one rule. You say the integral of f of x times g of x dx, it's not necessarily to have it f and g dash, is equal to what? The integral of one. So the integral, for example, of f of x dx times the other one without change minus the integral of the first one times the derivative of the second one. And usually you choose your j, the one that you're going to differentiate, for example, as a power of x, for example, x to the power n. When you choose x to the power n, so directly g dash will be smaller in degree. And you keep doing this until you finish, you deplete all the powers as of this algebraic function, and with this you have attained what you, the simple way of dealing with your integration by parts. And also we have shown you, of course, also a mechanical way of doing it. When you have a product of two functions, you construct a table by which you have two columns. One of the functions you keep integrating it, and the other one you keep differentiating it. And eventually, the one that you differentiated, somewhere it will end up somewhere, and then you multiply rows, inclined rows together until you finish up the integral. So this is, I hope, to have explained one of the methods that is very widely used, especially when you have two kinds of functions. For example, two kinds of transcendental functions like e to the power x times cosine x or logarithm x times x. In other words, one algebraic, for example, and one transcendental, even two transcendental functions. These kind of functions, the only way to deal with them is via the method of integration by parts. So at the end of this lecture, I hope to have succeeded in conveying to you this strong method of integration. And until we meet again, we remind you again of that the lessons are all uploaded to the site of the university, and I'm thanking you for your attention. And until we meet again, goodbye.